Hey guys, so today we're going to start chapter 15, which is equilibrium, and then chapters 15, 16, and 17 go very well together because it's all going to be types of equilibrium. I'm going to split 15 and 16 and probably 17 each into two sets of videos. Okay, so remember dynamic equilibrium, that's when the rates are the same. Also, we're going to start encountering more of this double arrow. We saw that for the first time in chapter 14, but it's really going to be from here on out where we're going to use the double arrow most of the time. And that just indicates that we're in equilibrium. We will be talking about the equilibrium constant a lot. So just note for this one, it's a capital K. All right, and then a large value K just means that we've got a high concentration of products. So that means there's going to be more products than reactants. Also, just remember the double arrow does mean the reaction is reversible. It could go either way. And a single arrow will indicate that it's only going in one direction. Reactants are going to products. I do want y'all to note the reactants are always still going to be on the left side, and the products are still going to be on the right, regardless of what kind of arrow I have. Okay, and here's that. Just remember dynamic equilibrium, that's when those rates are equal. So when we've got that flat slope for the forward and the reverse rates. Okay, rates are equal. It really wants you to know that. Y'all, there will probably be a question on the quiz or the test about what dynamic equilibrium is, so make sure you know. Okay, just because the rates are equal does not mean that the concentrations are equal. It only means that they're transferring back and forth at the same rate. Okay, this is going to be super, super important. So every time we write our K expression, or equilibrium expression, that's what this whole thing is called, it will always be products over reactants raised to their power. And the power comes from the coefficients from the equation. Also, K is called that equilibrium constant, and it does not have units, so that's a plus. We don't have to worry about units this round. Okay, so here's just an example. Notice we've got the products on the numerator part of our expression, and if there's a coefficient, it becomes the exponent. Also recall that brackets mean molarity. Okay, and there's our coefficient for our reactant. All right, so now we're going to do a couple practice ones. We've got K is equal to our products, CO, no exponent, H2 squared, all over methanol, no exponent. Okay, so it's really not too bad. It's always just going to be products over reactants. Okay, let's do this bottom one because I know that one gave you the answer. K is equal to what? Carbon dioxide, and it's raised to the third power because of the coefficient, and water is raised to the fourth. And then we've got propane, no exponent, and oxygen raised to the fifth power. So it's always just going to be products over reactants. Okay, it is really important that you know how to write that equilibrium expression, but it's also important you know what K means. So if K is much greater than 1, that's what that 2 greater than symbol is going to indicate. That means there's more product molecules than reactants, and it's going to be a lot more. If it's just greater than, it's going to favor the products, the equilibrium will. And so there's still going to be more products than reactants, but it's going to be not as much more. If it's much less than, K is much less than 1, then more reactants are present than products. And then if it's less than, it just is going to favor the reactants. Okay, when the reaction is written in reverse, that means the equilibrium constant K will be inverted, which means it's going to be 1 over K, and you can see that at the bottom. So there they flip the reaction from the blue reaction to the red reaction, they flip them, which means our equilibrium expression also flipped, so it's the inverse. So K forward is equal to 1 over K in the reverse reaction. If we multiply our equation, that means our expression is raised to that power. Okay, so that also means K can be raised to that power. So here we multiplied our first equation by 2, so our whole expression got squared. That means our K value also got squared from 1 to 2. And the last thing, if you add the equations together, then you multiply their K values. All of these could be on a quiz or test, so make sure you understand this. All right, so here we have an example. And again, really you need to look at what is happening. So here I see that N2 is a reactant, but on the bottom one, it's a product, which means I flipped my reaction. So I've already got to do 1 over K. Also notice the coefficient is different. It's halved from the first reaction to the second one. So we're going to have to square root it, which is raised to the half power. Okay, so we're going to do 1 divided by the square root of 5.6 times 10 to the 5. Grab my calculator. And I get K, the new K is 0.0013. And remember, they don't have units. Okay, let's just do one more together. So here we see that the reaction is flipped because here's our COF2 as a reactant. On this side, it's a product, but it's also doubled. So I'm going to do 1 over K, then I'm going to square K. All right, so I'm going to do 1 divided by 2.2 times 10 to the 6, but I'm going to square that value. And so I've got 2.0, really 2.1 times 10 to the negative 13 now. Oh, we probably need to do this one too. I wasn't planning on it. But this one is one where we add. So this is very important because this is that Hess's law I was talking about in chapter 14 that's going to reappear when we do chapter 18. Okay, so we're trying to get that top equation, and I need to manipulate those other two equations to make them look like the top one. The best way to do that is to find the most unique thing. So here, my methanol is pretty unique, and here it's there. It's also on the correct side, so I don't have to do anything to this bottom reaction. It's good. However, the top one has water in it as a product. On this one, it's a reactant. So I have to flip it. So it's going to be CO2 plus H2 yields CO plus H2O. Once I flipped it, that reaction goes away, and this becomes is equal to 1 over 1 times 10 to the 10 to the positive 5. which is just 1 times 10 to the negative 5. Okay, now we cross the things out that are the same on both sides. So my CO disappears, and my H2 adds together to be 3, which is what we have at the top. CO stays, water stays, methanol stays. Okay, so once we've got our equations and we can add them together properly, which is what I can do now. So K1 is going to be equal to the new K2 times, that's why it's a new one, K3. So I'm going to do 1 times 10 to the negative 5 times 1.4 times 10 to the 7, and I get 140. Okay, that is the worst these manipulating equilibrium expressions get. All right, so one thing we need to keep in mind is that we've been doing all this with concentration, which again is molarity, but we could also do it with pressures. Okay, I do want you to note the pressures must be in atmospheres. I believe there's a homework question where the pressure is not in atmospheres, and it really needs to be because it comes out wrong if it's not. So just something to keep in mind, there's 760 torr in 1 atmosphere. Also, torr is the same as millimeters of mercury. Okay, there's our pressure is always in atmospheres. This is the equation we're going to use to get back and forth between the two. Okay, this R value is the gas law R. It's not the one from activation energy. So this is the that's the activation energy one. 0.0821 you can use. And then temperature is always going to be in Kelvin. And remember, Kelvin is 273 plus Celsius is Kelvin. Okay, that delta N, that is the difference between the gas moles of reactants and the gas moles of the products. So it's still going to be products minus reactants because it's final minus initial. Okay, so here we have our problem, and remember it's Kp is equal to Kc RT delta N. Okay, the first thing you should always do is look for delta N, because if you know delta N is 0, you don't even have to do the calculation. So delta N is not 0. If we look here, I've got 2 moles of gas on the product side and 3 on the reactant side. So my delta N is going to be 2 minus 3. So my delta N is actually going to be -1, which is okay. All right, so I've got Kp is 2.2 times 10 to the 12, and that's equal to Kc, which I'm looking for. And I've got R 0.0821 times 25 Celsius, which is 298 Kelvin, and that's to the -1 power. So to get our Kc by itself, we need to divide 2.2 times 10 to the 12 by 0.0821 times 298 to the -1 power. And I get that Kc is 5.4 times 10 to the 13. Again, remember, no units are required. And they got the same answer as us, which is great. Let's do one more just so you can see. So this one's a little different. I've got Kp equals Kc RT delta N. Don't forget, RT is in parentheses. Okay, and always do your delta N first. This is 2, this is 2. Once you see that they're the same, that means Kp is equal to Kc, because anything to the 0 power is 1. So this one, I don't even have to do the calculation. All I have to do is rewrite it. I know that it's the same. All right, so for which of these reactions does Kp equal Kc? So again, we're looking for the one that's 0 moles of gas. I only care about the gas. So here I've got 1 minus 2, so that's -1, not equal. And I've got 3 and 3, that is equal. And I've got 3 and 0, so this is 3. So the one where they're going to be equal is when delta N is 0, where the moles of gas are equal on both sides of the reaction. Okay, another thing I need you to know is that solids and liquids are not included in our equilibrium expression. So only gas and AQ. Okay, those are the only ones. We leave liquids out completely, and if you look at this reaction, they did not include this liquid water. Okay, also, if there are ions present, you do have to reflect that in the expression. Okay, so here if we were to write the equilibrium expression, it would be K is just CO2 on top and CO squared on bottom. All right, so here we have one. Again, solids and liquids don't count. So this equilibrium expression is just CO2. See one more, liquids and solids don't count. So K is equal to only Cl2s on top. But we've got HCl on the bottom, not squared to the 4th, and O2 on the bottom. All right, so now we're going to start calculating the expressions. Actually, you know what? We're going to stop here, okay? So we'll pick up next time on this screen. Y'all have a good day.